Hey guys, we're going to go over the Vsepr shapes, and we're going to be on page 9 of your packet. So it's going to look like this page right here. There are 5 shapes that we need to know. So our first shape is going to be the linear. So it's called linear, and big surprise, it's linear because it's in a line, as you can see here. So the total pairs of electrons, that's going to be any kind of lone pairs, which are your dots that you would see on a Lewis structure, or the bonded pairs, which are the lines. With a linear structure, there's going to be 2 total pairs of electrons, and they're both going to be shared pairs. As you can see here in the structure, we've got a bonded pair here and a bonded pair here. There are no lone pairs in a linear atom. The hybrid orbitals, those are just which orbitals are going to be coming together to allow those bondings to happen. And this is going to be an sp hybrid orbital. This is just something that you have to memorize, nothing else about why those or how those come together. The angle from the central atom is going to be 180 degrees as seen in this picture. Remember, all of the electrons are negatively charged. They all try to get as far away from each other as they can in this structure. So in order to get as far away from each other as possible in a linear structure, that would be 180 degrees away. The classic example for this one would be CO2, because with carbon dioxide, we've got a pair of electrons bonded to the oxygen and a pair of electrons bonded to this oxygen. Even though there's dots on the oxygens, those are not on the central atom, and so we do not count those as lone pairs. Lone pairs would only be on the central atom itself, okay? Here, I'm going to show you some structures here as we go. So this would be a linear atom, okay? You have your one central atom, you've got your 2 bonded atoms to that, and it's all right there in a line to get those bonded pairs away, as far away from each other as possible. The next one we're going to go over is, and I'll show you first before we, before I share my screen again, is going to be the trigonal planar, and it looks like this one here. So as you can see with this, you've got your one central atom here, you've got 3 bonded atoms to it. Okay, and they're all trying to get as far away from each other as they can. And this is a trigonal planar. You can see it's all in a line, any way you look at it, like this. So let me get back to this notes page here. So this was called, like I said, trigonal planar. The prefix tri, of course, means 3. So with the trigonal planar, there are 3 total pairs of electrons, and those are all shared pairs. So you've got 1 here, 1 here, and 1 here, and there are no lone pairs of electrons. The hybrid orbitals are going to be sp2. If you're trying to remember your hybrid orbitals, when you add up your superscripts, they should equal your total pairs of electrons. So S, no subscript, or superscript means 1. So 1 plus 2 is 3, and that equals our total pairs, okay? The angle from the central atom in a trigonal planar is going to be 120 degrees. And a classic example of this would be the COCl2 that we drew during our Lewis structures, because we have our carbon in the center, double bonded to the oxygen, and then our chlorines bonded to that carbon as well. No dots on the carbon indicate that there are no lone pairs of electrons. Next one we have, as you can see in the picture here, we have 4 things, 1, 2, 3, 4 bonded to it. This one is called tetrahedral. And because the prefix tetra means 4, that means there are 4 total pairs. All of those are bonded. So there are no lone pairs of electrons here. The hybrid orbitals then are going to be sp3, 1 s and 3 p's added together equals 4. And our angle is going to be 109.5 109.5 degrees. 109.5 degrees. Classic example of this one would be methane, which is CH4. Carbon in the center and 4 hydrogens around the structure to form a tetrahedral shape. Right, so let me show you the model of that. My tetrahedral is right here. As you can see, there's one central atom here. There are 1, 2, 3, 4 atoms bonded to it to make this tetrahedral shape, and they are as far away from each other as they can get, which is why the angle is 109.5 degrees from the central atom. All right, so the next one we have is trigonal pyramidal. So let me show you this first. I'm gonna pop this thing off here. Trigonal pyramidal, kind of like the planar, it has 3 things bonded to it, but there is a difference because as you can see, the structure is different than the trigonal planar, which is this one. The reason why this is different, even though this has 3 bonded pairs and this has 3 bonded pairs, is because the trigonal pyramidal has a lone pair of electrons. This represents the lone pair of electrons. The lone pair of electrons take up a lot of space around the central atom, and as such, it pushes these bonded pairs down to make more room. So that's why it changes the shape from the trigonal planar. So let's go ahead and put this information down. So this one is the trigonal pyramidal. Now this one has 4 total pairs. As you can see in the picture, there's only 1, 2, 3 bonded pairs, 3 shared pairs. There's going to be a 1 lone pair of electrons. So you would see some dots on the central atom pushing these 3 bonded pairs down. Because there's 4 total pairs, the hybrid orbitals are going to be the same as the tetrahedral, which is sp3. You don't have to know the specific angle on this one, just know that it's less than 109.5. And ammonia is a classic example of this one because you have nitrogen in the center, you have your 3 hydrogens bonded to it, and you have the lone pair of electrons here that push those 3 bonded pairs down. Our last example is called bent. And bent, as you can see, it has some similarities with linear in that it has 2 bonded pairs. It has 2 bonded pairs. The reason it's not in a line anymore, though, is because that there are lone pairs of electrons here. There's lone pairs of electrons on the central atom, making it have 4 total pairs of electrons. Because it has 4 total pairs, the hybrid orbitals would be the same as tetrahedral, which is sp3. The angle, again, you don't have to know the specific. It's going to be less than 109.5 degrees. And the classic example is going to be water, H2O. O is in the center. You've got your hydrogens bonded to it. And you have your 2 lone pairs on the oxygen pushing those hydrogens down. Okay, so let me show you my structure of the bent, which is here. As you can see, it's got these 2 fan things here that represent the lone pairs of electrons. It has 2 bonded pairs here. So because it has those 2 lone pairs of electrons, I'll just pop those off for a second. It looks different than the linear structure here. Linear has no lone pair, so it's all in a line. But because the bent had those 2 lone pairs of electrons, it pushes those bonded pairs down and makes this bent structure. Okay? So you should always draw your Lewis structures before you determine what the Vsepr shape is, because you need to know if there are lone pairs on the central atom or not. Lone pairs will determine if it's linear or if it's bent. Lone pairs would tell you if it was trigonal planar or trigonal pyramidal. It's important to know that before you make your determinations. All right, let me know if you have any problems identifying the Vsepr shapes.